Around 1,500 feet, the margin for indecision collapses in a dive bomber. Above this altitude, a pilot may have seconds to troubleshoot a failing engine, cycle fuel selectors, or attempt a restart. Below it, the aircraft's energy state shrinks so quickly that diagnosis becomes a luxury the airframe cannot afford. The physics of the dive demand a commitment. Pick a landing surface and fly the touchdown. On May 28, 1945, Ensign E.D. Fraser crossed that practical threshold over San Diego County. He was piloting a Curtiss SB2C-4 Helldiver, Bureau number 19866, assigned to Bombing Squadron 14. The aircraft was in a steep practice dive when the right twin Cyclone engine quit. The massive 14-cylinder radial engine went silent, instantly converting the 11,000-pound bomber into a glider with poor lift characteristics. Fraser attempted to regain power, but the altimeter confirmed the loss of energy was irreversible. With a passenger, Army Technical Sergeant Joseph Metz, in the rear gunner position, Fraser aligned the aircraft with the surface of Lower Otay Reservoir. He executed a controlled ditching, bleeding off airspeed just above the water before settling the heavy airframe into the lake. Both men exited the cockpit and swam to shore. The Helldiver, intact but flooded, pitched down and began a slow descent to the bottom. It vanished into the dark water, and a 65-year silence began. For most of that time, the aircraft's exact resting place lived more in local rumor than in verified hydrographic data. Otay was an operational reservoir, its bottom hidden under deep, fluid mud. Year by year, the Helldiver settled deeper until it became a fixed geometry on the lake bed. The transition from a lost airframe to a localized target occurred in early 2009. Two fishermen, Dwayne Johnson and Curtis Howard, were drifting the reservoir with a consumer fish finder running. Its display traced the bottom in simple acoustic slices, flat mud, then a sudden hard return that didn't fit. Too regular for rock and too large for casual debris, it read like structure, not geology. That electronic return closed the loop on the 1945 loss. The coordinates matched the historical vicinity of Fraser's ditching, but a sonar hit is not an identity. In freshwater sites, targets are often trees, debris, or sunken barges. Verification requires contact, and at roughly 90 feet, this was beyond casual diving. The objective was clear, but the constraints were absolute. To retrieve the Helldiver, a recovery team would have to work where visibility doesn't exist. The Navy still owned the aircraft under the principle that military wrecks remain government property, and the National Naval Aviation Museum authorized A&T recovery to turn a blip into a recovered asset. The problem was simple to state and brutal to execute. Plan a heavy lift for a fragile structure you can't see. Every connection, every strap, every hazard check done by touch. The evidence available to a recovery team is defined by two physical filters. The first is the kinetic energy of the crash, which determines if the airframe remains a single structural unit or becomes a debris field. The second is the chemical environment of the resting place, which dictates whether that structure survives the decades or dissolves into oxide dust. In the case of Bureau number 19866, both filters align to produce a statistical anomaly. The aircraft on the bottom of the Otay Reservoir was not a wreck in the traditional sense. It was a suspended artifact. The survival of the airframe began with the pilot's management of impact energy. When the 1,900 horsepower engine failed, the aircraft lost its ability to maintain altitude, but it retained its mass and forward velocity. A ditching is a controlled collision where the pilot must dissipate this kinetic energy against a water surface that becomes effectively rigid at high impact speeds. If the angle of attack is too steep, the deceleration forces exceed the structural limits of the aluminum skin, causing the fuselage to buckle or snap behind the wing root. Pilot Fraser executed a precise energy bleed. He brought the Helldiver down just above stall speed, holding the wings parallel to the water. This geometry allowed the water to absorb the forward momentum over a longer distance, keeping the deceleration loads within the airframe's design limits. The bomber stopped floating and began to sink, but it did so as a complete, integrated machine. As the aircraft descended 85 to 90 feet to the reservoir floor, it entered a low-light, low-circulation layer near the bottom. In marine salvage, the greatest enemy of aluminum is the combination of saltwater electrolytes and dissolved oxygen, which accelerates galvanic corrosion. The Otay Reservoir removed the salt electrolyte, and the aircraft's resting place offered limited circulation. More importantly, the bottom was covered in a deep, fluid layer of silt. This silt acted as an encapsulation mechanism. When the heavy aircraft settled, it did not rest on top of the mud, it sank into it. The semi-liquid sediment flowed over the wings, the fuselage, and into the open cockpit, creating a thick, impermeable seal. This created a local, anaerobic environment. Without the circulation of oxygenated water against the metal surfaces, the chemical process of oxidation was arrested. The mud blocked all light, preventing the growth of biological organisms that typically consume fabric and paint. The deep silt effectively froze the aircraft's condition at the moment of submersion in 1945. The result of this silt encapsulation was a preservation paradox. In places, the original 1945 finish could survive beneath the mud, and components that are usually lost early were still present. Some fabric-covered control surfaces, often the first materials to fail, remained in place. Inside the cockpit, portions of the instrument panel and its gauges could still be read once cleared, their glass faces surviving better than most underwater aviation archaeology would predict. The environment had acted as an unintentional preservation vault, keeping the aircraft unusually complete for its age, but not untouched by time. But that same preservation came with a price. The silt that sealed the aircraft from oxygen also sealed it from sight. Any movement turned the water into a total blackout, and the divers would be forced to work inside a fluid as thick as pudding, surrounded by evidence they couldn't see. The mud had saved the Helldiver, and it was now the thing most likely to keep it there. A remote sensor can give you a set of coordinates, but not a certainty. A hard return is only a silhouette. It can hint at size and edges, but it cannot tell you what the metal looks like, what's wrapped around it, or what will fail under load. At roughly 90 feet, the only way to turn that mark into an aircraft was contact, skin to skin in black water. To resolve the identity of the target, the A and T recovery team had to deploy divers into the reservoir. Past 30 feet, the light thinned. By 60, it was gray twilight. At 85 feet, the working depth, suspended silt closed the world down to inches. In that blackout, electronics could outline shape, but they could not certify safety or structure. The fisherman's device had produced a sonar target, a return that relies on the geometry of sound. The transducer emits a pulse of acoustic energy that travels through the water and strikes the bottom. When this pulse hits a hard, vertical object like a fuselage or a vertical stabilizer, it reflects back to the sensor, creating a bright highlight on the display. If the unit is capable of side imaging or scanning, the return can also produce a dark void behind the object, an acoustic shadow, where the sound is blocked. The shape of that shadow can hint at height and width, but it cannot reveal the condition of the metal, the presence of entanglement hazards, or the integrity of lifting points. It provides a silhouette, not a diagnostic report. The divers arrived at the bottom and switched to a tactile survey mode. In the black water, they could not see the aircraft they were inspecting. They had to build a mental model of the wreck solely through touch. A diver would reach out and contact a cold, smooth surface. By running a gloved hand along the metal, he could determine the curvature of a wing leading edge or the flat panel of a fuselage section. He had to differentiate between the organic feel of a submerged log and the manufactured precision of riveted aluminum. Moving hand over hand, the lead diver traced the outline of the structure. He found a tail section rising from the silt. He followed the fuselage forward, confirming it was largely intact and not a scattered debris field. He located the cockpit area, feeling the canopy structure still in place. The tactile inspection built a picture of a large, single-engine aircraft consistent in scale and geometry with a Curtiss SB2C Helldiver. The contact was strong, but in a black water site, type confirmation is not the same as serial number proof. The final link would come later when cleaning exposed identifying markings and the airframe data plate. Recovering the Helldiver meant pulling hard enough to overcome gravity and bottom grip, without letting the rigging turn into a cheese wire against 65-year-old aluminum. The aircraft's factory empty weight was approximately 11,000 pounds, but the working lift was heavier, the fuselage was flooded, and the wings were buried in dense sediment. The team was not just lifting a machine, they were fighting the reservoir floor itself. The primary adversary in this equation was suction load. When an object with a large surface area, such as a wing, settles into fine silt, the interface between metal and mud can behave like a seal. Lifting force must overcome not only gravity, but also adhesion, and the pressure differential created as water is displaced and flow paths are restricted. This effect can add thousands of pounds to the effective load. And when the seal finally breaks, the release can be abrupt, shock loading the airframe and the rigging if the lift is not carefully controlled. To mitigate the risk, the divers had to rig the aircraft across the strongest coordinates, the wing roots and the engine mount. But in zero visibility, there was no clean swim down and attach. Every move had to be done by feel, building a mental map one panel line at a time. The team had a name for it: Braille diving, rigging by touch, one panel line at a time. The rigging process required the team to pass heavy lifting straps underneath the fuselage and wings, which were buried deep in the mud. To do it, the divers used water flow and handwork to loosen compacted silt, relieve suction, and clear paths beneath critical structure. In total darkness, they worked by touch, guiding lightweight lines under the airframe, and then using those guides to draw heavier lifting slings into position. It had to be repeated for multiple attachment areas, all while working blind in a suspension of blinding silt. Once the straps were in place, the team had to manage the lift geometry. If lifting cables angle inward toward a single hook point, they create compressive forces that can crush a thin-walled fuselage. To prevent this, the recovery team used a spreader bar or multi-point bridle arrangement to keep the lift line separated and as vertical as possible. This geometry directs stress into the spars and bulkheads, structure designed to take load, rather than concentrating it into the skin, which is not. Before the main lift could commence, the team executed a preliminary disassembly to protect the most fragile components. The sliding canopies, which were in excellent condition, were at risk of shattering during the extraction. Working in the dark, divers carefully detached the canopy rails and recovered the glass sections separately. With the glass safe and the straps threaded through the mud tunnels, the rigging was complete. The Helldiver was no longer just a target in the mud. It was a suspended load connected to the surface, ready to test the strength of the airframe against the grip of the bottom. The boundary between the water and the atmosphere is a hard geometry limit for a recovery operation. Below the surface, buoyancy supports part of the airframe, reducing the effective tension seen by the rigging. At the moment the structure rises out of the water, that buoyant assistance disappears and load transfers rapidly back into cables, straps, and attachment points. Gravity applies its full force, and any retained water or adhering mud can push the lift well above the aircraft's dry weight. On August 20th, 2010, the recovery team prepared to move the Helldiver across this critical threshold. The lift plan dictated a slow, incremental ascent. The crane operator applied tension to the spreader bar, taking the slack out of the nylon straps that were threaded through the mud tunnels. The aircraft broke free from the suction of the sediment, a moment that usually registers as a sharp spike on the load cell. Once the adhesion was broken, the Helldiver began to rise through the water column. The lack of visibility meant that the team on the barge could not monitor the attitude of the aircraft visually. They had to rely on the geometry of the rigging to keep the bomber level as it ascended from 90 feet toward the sunlight. As the propeller hub breached the surface, the operation paused. This was a mandatory hold point. The fuselage of the Helldiver was not sealed. It was flooded. The internal volume of the aircraft, from the engine firewall to the tail cone, was filled with water. If the crane hoisted the aircraft completely out of the reservoir in one motion, the weight of that trapped water would be catastrophic. Water weighs approximately 8 pounds per gallon. A flooded fuselage contains thousands of pounds of liquid mass. The aluminum skin and the bulkheads were designed to handle aerodynamic loads, not the hydrostatic pressure of being a water tank. Lifting too fast would cause the fuselage to burst or the wings to fold under the sheer mass of the fluid inside. The crane held the aircraft at the waterline, allowing it to drain. The water poured out of the open cockpit section where the canopies had been removed during the dive phase. It streamed from drain paths in the wing roots and the tail. The team watched the load scale drop as the aircraft shed its liquid ballast. As the mud washed away, dark blue navy paint emerged for the first time in 65 years. The markings began to resolve, and while surface corrosion was visible, it appeared far less severe than the aggressive damage that plagued saltwater wrecks. The wings remained attached to the fuselage throughout the lift. This was a deviation from many recovery standard operating procedures, where wings are often removed underwater to reduce drag and width. However, the integrity of the wing root bolts and the strength of the spar allowed the Helldiver to be recovered as a single cruciform shape. The spreader bar performed its function, keeping the straps vertical and preventing the wings from being crushed inward toward the fuselage. Once the drainage was sufficient to bring the load within safe limits, the crane completed the lift and lowered the aircraft onto a custom-built cradle. The Helldiver was finally out of the element that had hidden it for 6 decades, but exposure created a new clock. If mud and trapped moisture were allowed to dry in place, oxidation would accelerate fast. On deck, the priority was immediate. Keep it wet, keep it controlled, and keep the crust from forming. The process required to slow this degradation is conservation stabilization. The team kept the artifact wet and began controlled cleaning immediately, sluicing sediment away before it could shrink, harden, and lock moisture against the skin. This was not cosmetic work, it was triage. An early stabilization step meant to slow the first surge of corrosion after recovery. As the layers of sediment were sluiced away, the team could finally verify the aircraft's identity. The airframe data plate emerged under the mud, stamped with the bureau number 19866. That single mark tied the recovered machine to Ensign E.D. Fraser's ditching on May 28, 1945, and to the records that documented the engine failure. With the proof in hand, the cockpit was next. With the mud gone, the payoff was immediate and unnerving. The cockpit looked like it had been sealed in a vault. The instrument panel held its black finish, dials and gauges sat intact behind unbroken glass, needles frozen at their last indications. Fabric control surfaces, materials that usually fail early, were still tight and structurally sound. The deep silt had done exactly what theory predicted, delivering a specimen that needed conservation, not reconstruction. This level of preservation is statistically significant given the production history of the type. More than 7,000 Helldivers were produced during the war, depending on how totals are counted across manufacturers and variants. Despite that volume, very few examples survived the scrap drives of the post-war era. The recovery of Bureau number 19866 added a nearly complete airframe to a global inventory small enough to count on a few hands. It represented a massive injection of original technical data into the historical record. Following stabilization on the barge, the aircraft was prepared for its next movement. It was transported to the National Naval Aviation Museum in Pensacola, Florida, where long-term conservation could begin under institutional control. Years later, the project would be transferred to the USS Midway Museum, eventually housed in Hangar 805. The goal was never to fly it again, but to hold it steady as a static exhibit, an intact lesson in wartime engineering. What started as a hard return on a fish finder ran a gauntlet of zero-visibility rigging, suction loads, and fragile lift geometry, and ended with a verified national asset on deck. The Helldiver is no longer a rumor in the mud. It is a documented volume of history retrieved by engineering discipline and the calculated management of risk.